Hey, Japanese Math and History, and we are going to take a look at free body diagrams. So, what we're going to do is we're going to do an introduction. So, there is one little issue. That green box right there, or that green cube, is not in the right place. And the problem is, it has to be moved past that red marker. But how are we going to push that block? Well, what we do have is a robot over there, which is going to push it. So what's going to happen is the robot's going to open its claw. It's going to drive over to the thing, grab it, and push it to the other side. But there is a problem when I explain that story, is when we talk about physics, how are we going to understand and tell other people what just happened and what forces were on it? So that's why we are going to use free body diagrams. So many physics people and those who love math, especially the ones that love engineering, when we work with different engineers, whether it's science related or if it's mechanical related or aerospace, blah, 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 then you will work in a bunch of teams. But the problem is sometimes those so-called teams don't speak the same language. Not everyone on this earth speaks English. So what happens is they designed a new way of describing what happened to that robot and what happened to that block and how to describe it for its forces. So what we're going to do is, yes, we are going to make a block, mostly a rectangle. And what we're going to do is put a little dot in the middle. So that is explaining that there is an object right on the piece of paper, and we're thinking about that object. It also explains that there's a dot telling us that is the middle of what's going to happen. The first thing we got to think about is what just happened and what forces just happened. Well, when the block was literally standing, or when the block was literally right there, there are two forces right away that we can see what has happened, or two forces right away that we looked at or spotted. A, there's a force that's pulling the block down to the ground. And the crazy thing is, it's very simple. That force is going to be the force of gravity, the force of Earth's gravity. So we make a line from the middle and drag it down to the ground, representing that there's a force pulling the block down, or pushing the block down. And that is the force of gravity. The other thing is, that block is not being smashed to the ground, or it's not a blob where it lies flat like a piece of paper. So there's another force that the block is doing to keep itself stay up still. And that is pushing it up. And that is going to be the force of norm. So normal force is explaining how much force does the object require to keep itself standing up. Because if we didn't have that so-called normal force, then we would all be blobs and we couldn't really move anywhere. So those are the two forces that we've seen already. But hang on, what happens if we see that robot do what it just did earlier in the video? So I put the robot back to where it was. The robot goes up to the block, gets the claw, grabs it, and pushes it forward. The robot pushing the block forward can also describe what has happened to the block's motion. The block is going to go to the right, so we're going to put a line from the middle to the right. And that is going to be the force being applied. So that is telling you that the robot pushing on the block is telling you that there's gotta be some kind of force pushing the block that way. Like I'm applying force on that block right there. But there's one more force that you can't see. You can't see gravity, but you can notice it. You can't see normal force, but you can notice it. And you can't see, well, you actually can see force being applied. That is going to be the opposite direction. The robot is not on an ice rink, so therefore there's going to be some kind of thing slowing the robot down, or keeping it from making it harder to go faster. And that is called friction. Friction happens when there's some kind of object trying to rub on the floor. And we also need that friction to make this object stop moving. Like that. That ground created friction for that block to stop. So what happens is we have to do F of F. The force of friction is pulling the block the other way. So that is going to visualize the forces of what's happening on the block right now. But sometimes engineers and also people that love physics want to understand, well, okay, you described everything about forces, but how can we summarize if we have this project and it's due at like 11:59 p.m., how are we going to describe the block's movement without explaining all those crazy forces? What we have to do is do a more simpler diagram. So, of course, we will have that box. I get. But what we're going to do is only calculate the force of net. What is the net force? Or to summarize everything what we just said, where is the force going to go? And apparently, when that robot pushes the block forward, the block is also moving forward with it. So guess what? The force being applied is going to be not the strongest force, but the force that's noticeable that causes the block to move to the right or move forward. So our net force is talking about which force is making the block accelerate or move. So what we're going to do is do this. Our net force is going to go this way. So that is what the summary of what that in that version should look like. And that explains why free body diagrams can help communicate with other people, even though A, they don't understand that format, B, they speak another language, or C, to summarize what just happened without having to go blah, 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 and lecturize everything like blah, 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 blah. Thank you for watching Top in Your Life's Math Industry. Like and subscribe. Sometimes, solving problems like these are going to be very, very easy, especially for the so-called robot. But sometimes, when you're solving some other problems, it could be a little bit complicated. Sometimes, it could be way more complicated.